Looks like we can get started. Welcome back, everyone. Seems like a smaller class today, but I just assume people are tired after getting through the second exam. With what we've got going on today, we're moving through our chapter 11 on example 2 in section 11.2 with series. This is a bigger section because we're connecting the dots on how sequences work versus what goes on in the land of series, where we're adding together every single term of the infinite series. Then we're going to come up to the next section, an integral test, which we may finish on their next class. So that's where we're at so far. As for the second exam, I should have these graded. I'm going to begin grading them on Friday. I hope to finish them on Friday, but it looks like with the pace I'm going at so far, grading may continue into the weekend. But I'll post an announcement for them once grading is concluded so that you'll know those grades are posted. I'm also really hoping on the Pocatello Testing Center that they're able to get all their scans done and emailed back to me on time. The hope was having this exam after midterms should have been a little bit easier for them so that their backlog isn't so big. Well, any last questions, folks, before we get started today? Okay, let's jump in then. So in section 11.2, we didn't leave off here, but this is a good spot to start off. We're working a lot on sequences, but now when we convert over to the concept of a series, what we're doing is we're taking every single term from the sequence and just adding them up, adding up every term. You really can't do that. There's infinitely many terms and only finite time to add things. But what we mean is we're going to take a limit of this thing. This is the partial sum, where we take a summation from 1 up to n, but we let n get larger and larger so that this partial sum approximates the total sum, and in the limit, we say that they are equal to each other. So now the existence of the series, adding up infinitely many terms, it just sounds weird. This is going to converge or diverge depending on this limit of partial sums, which we refer to as Sn. So if the limit exists, then we say that this is a convergent series. And if the limit fails to exist for whatever reason, if it just doesn't exist as a limit right here, then we say the series is divergent. And here was our first example looking into an actual series, or I think it's our second example. It does say example 2. This was what we called a telescoping series. And the idea was when we go to this stage, saying that this is the limit of the partial sums, we then went over and just indicated this way. So Sn is just a different way of saying all of this right here. But we produced a formula for Sn. This is exceedingly rare, and our author mentions this a lot of times in section 11.3. Finding a formula for Sn is nearly impossible for a lot of situations. It's a new ad hoc method for every brand new series, so there's no formula to do this. But there's a 2 series where it works out, the telescoping series and a geometric series. So with the telescoping series, what we did was, for looking at Sn, that means we're going from I equals 1 all the way up to an n. So it's indicated here. We plugged a 1 inside here, just wrote it out. Plugged a 2 inside here, wrote it out. And as we wrote out all those terms and add them together, we notice that there is always cancellations. The first term survives 1, and the final term survives negative 1 over n plus 1. So we took all that information and we plugged it in right here. We're taking the limit of the partial sum still, but now we have a formula. This is the part which is extremely rare. When we take the limit, this part goes to 0. And so it tells us our total sum, not only does it converge, but we know the total sum converges to exactly 1. In other words, this is like the world's weirdest and most unfortunately complicated way to write the number 1. Lots of ways to write the number 1, and that's just one of them. But any questions or comments, folks, for that problem that we did before the exam? Okay, next thing we did was we looked into geometric series. They're not telescoping, but if you do the right formulaic thing over here, you do get a telescoping formula, just like this stuff. So that's this next series down below. So a geometric series starts off like this. We have some value a, multiplying r to a power, which was referred to as a common ratio. Like before, this is the limit of the partial sums, which we wrote as Sn. When we went to write out this line for Sn, we're just coming into the formula and plugging in a 1 to start, then a 2 and a 3 and so on. When we plugged in a 1, this is r to the power 0, so that's why r was gone. And we only went up to r power n minus 1. Then we just multiplied the last equation by r, got all these terms, most of them matching. And then when we wrote this line, Sn minus r times Sn, that should remind us of the telescoping series. Only the first term survives and the last term survives. So if you have a formula for Sn, you can take the limit of that thing. But here's where it got a little finicky. That limit does not exist for plenty of values of r. So we cited theorem 9 from section 11.1. We have convergence when r is between -1 and +1, and it converges to 0 as well. So in the limit, that whole thing is gone, provided r is between -1, +1. And geometric series has, in this case, a total sum, a divided by 1 minus r. And that's the exact sum of the limit. So these are really just the two situations in series where we can give an exact formula for total sums in this kind of way. It's not as if getting a total sum for a series is impossible, but it takes a fantastic amount of work, even for something simple like this. Our book mentions this one in section 11.3, that Euler found a formula, a way to do this. He used complex numbers, complex analysis, and showed that this was something like pi squared over 6, some random value. He didn't do it this way. He just found a crazy formula that could convey this information into complex numbers. So that's a spectacular amount of creativity for just 1 over n squared. But we should take advantage of the things we have, the tools that work, and that's the geometric series. The geometric series test says you're convergent when the absolute value of the common ratio is less than 1. So it's all about this part right here. Coming from that part r in the formula for the series, if r is greater than or equal to 1 in absolute value, we have a divergent geometric series. And a lot of these things are in red because I revised these notes probably like a dozen times, trying to pick out the right problems. Well, any questions at the moment, folks? Okay, example 3 is kind of a reminder and just extra practice. It's a throwback to when we were in section 11.1, we did this problem. We were given just a random sequence, not a series because they aren't being added up. These are just comma-separated values. And we had to come up with a formula for that sequence. After we did that, we could have taken the limit of it if we wanted, but it looks like that's where the problem ended. The purpose of this kind of example is we actually have to do that plenty in these notes for homework problems and occasional exam problems. So let's work on this one here. We're adding together infinitely many terms that follow this pattern based off the first 4 terms we were given. Now, I have to admit to you, there's a lot of sequences that match these first 4 terms. We're just going for the most obvious pattern. So we're going to call this a summation as n goes from 1 to infinity of an. We can discover a formula for an, and if it turns out to be something nice like a geometric series, which is what we're expecting, that's what the instructions indicate, then we're just going to look into the common ratio and decide the problem from there. But by the way, as you look at the terms, does it look like it converges or does it look like it diverges? Kind of hard to assess, but one thing you can imagine is convergence means that these numbers that you're adding should be getting closer and closer to 0. Well, when we take the first 2, we are getting a +3. This is going to make it pretty large negative. This is going to make it pretty large positive, but then it just keeps on alternating just like that. It's actually kind of hard to resolve that if it would settle down on something, but that's why we can now come up with the formula for the nth term and analyze it a totally different way. So to help with that analysis, think of -2 as a1, 5 as a2, and so on. So 1/25 fourths is a4. Down below, we want an. And this is the essentially trial and error process of coming up with the nth term of the sequence. There's no formula for this. This is really just analyzing what you see and going from there. So what we see for sure is the signs alternate. So if you like, you could start off by saying -1 to a power of n. The power of twos are confusing. This is 2 to the power of 1 with a negative sign. I guess you could say 2 to the power of 0. Now, it's in the denominator. That's 2 to the power of -1 if it was in the numerator. So we can come back to the 2. Let's focus on the 5. It looks easier. That's 5 power 0 times 2, 5 power 1, 5 power 2, 5 power 3. So it looks like we can say 5 to the power n minus 1. Reason I went n minus 1 is we plug in 1 first to get our term a1. We plug in 1 here, we get the negative sign. Plug in 1 here, it's 5 power 0, so there's no 5s. As it should be, all we're getting is -2. So now we come down below. We need to get the right power on base 2 so that it shows up in the numerator, it's gone on the next step, and then it starts showing up in the denominator. Anyone see what it could be for down here? I think that's a good call. Let's test this out. N minus 2. Honestly, for a lot of these things, I don't know if it's going to work until I write it down and I just try it. And then I know if I have to make an adjustment or not. So it's truly, in the strict sense of the word, trial and error. But I think that looks pretty good. Let's test this out. If we compute a1 based on that formula, we'll get -1, 5 power 0, 2 to the power of plugging in 1, so -1. 5 to the power 0 is just a 1, and you can bump the negative exponent up into the numerator. Yes, I didn't need a fraction bar, and call that -2. So that really works out to get that 2 there. Next, let's try out another one, a2. That's going to convert this to positive, so we don't have a negative sign. That'll be 5 power 1. Down below, it's 2 power 0. So we get a 5 out. At this stage, I'd probably be totally convinced we have the right thing. Let's try just one more. So A3. If we've got A3, I'd say we really have the formula. We're plugging 3 here, so it's negative. 3 here gives us 5 power 2. 3 down here gives us 2 to the power of 1. And sure enough, that really is -25 halves, if I remember to put in the 2 there. So we nailed term A3 rather. And let's do the method of eyeballing it on term A4, now that we're probably more convinced. 4 there's positive, 4 there's 5 power to 3, which is 125. A 4 there is 2 to the power positive 2, which is a 4. So it looks like we have the right formula here, which means we can proceed on this step. Well, any questions, folks, to that stage? Okay, well, before we just drop it in where an is, notice we're trying to make it look like that. There's a couple requirements we want. We want our common ratio r to not be spread out like this, and we need our exponent to be to the power n minus 1. So now we're combining the 5 and the 2 here to a common exponent, but now there's also an exponent mismatch. We need to increase that to a power 1. So let's do a little bit of work on this and say, well, maybe even an additional step where this is power n, that should be power n minus 1 as well. So let's factor away a negative sign. Now it's -1 power n minus 1, 5 to the power of n minus 1. And if you want to increase this exponent, you have to go like this. Looks weird at first, but just think about properties of exponents. Make it 2 to the power of -1. That's what we wanted. To make it totally correct, you have to divide by 2. That's because this is the 2 to the power of 1, and when you do a division, exponents would subtract. This would become an n minus 2 when we combine those bases. So now it's an even bigger mess, but here's where it cleans up. The 2 way down in the denominator, if we multiply by the reciprocal, just promotes it up here for -2. The rest of the stuff has power n minus 1, so we can just drop it in. this way. -5 halves power n minus 1. So once we have all that, we're going to plug it into this original series right here. But I think we should take an additional space so we know where this is all going. So part A is a kind of a harder problem on this one because we had to come up with the actual form for the sequence, the nth term. Then we add them up over here. Now it's a series. And we can say that summation as n goes from 1 to infinity of an, where we left off, is now equal to this. N goes from 1 to infinity of -2, -5 halves to the power n minus 1. So we're just about ready to analyze the situation for that geometric sequence. Let's just carry this down for a quick reference. I mean, we just were looking at that formula. Looking at this formula again, our next statement we need to make is, what is the common ratio R? Anyone see what value it should be in this problem? The common ratio is this value right here that's being raised to a power. And it's kind of hard to see what it's conveying in this format. Exactly, it'd be the -5 halves. Another way to think of the common ratio is when it's expanded out, it's the power that keeps multiplying all the next terms. We think of it as a ratio between -1 and +1 if it's really converging. But that's why we call it a common ratio. You get to the next term by multiplying by the same value. Exactly. In this format here, it's the one that's being raised to that exponent involving n. Should be n minus 1 if we're about to use the formula for the total sum. So if it's not n minus 1, we have to do this kind of exponent work to force it there. But in either case, good call, the R value is this right here, -5 halves. Now, tragically, we worked hard on this problem, but this one doesn't converge. Convergence means in absolute value, you are less than 1. But this is less than -1, so that's not true on this one. So that tells us the series diverges by the geometric series test. Now, we knew we were using the geometric series test because the problem says it. Test the series, the geometric series for convergence and divergence. I usually write this at the end because a lot of our other problems in homework, when it doesn't say to use a specific test, we have to state the type of test we're using and whether it converges or not. So I'll always make a big deal out of that so we don't miss it when we're doing them as homework questions. But we did it, folks. This one is a divergent series. Not super easy to tell by the form of the terms, other than they're becoming either a large negative or a large positive. They're starting to get unstable. But down here, it resolves it once and for all. The common ratio was less than -1. That's right there what caused divergence. So that's the problem. Let's try this out all over again. This one is a little bit nicer because notice the nth term of the series is provided here. So we're just doing this right here and analyzing. Oh, I wanted to put that screenshot down there. But to really make this work out, there's still a couple problems. We really need the n minus 1 for one thing. We don't want two things being raised to an exponent. So once again, we have to do some exponent work on this thing. Starting with the 2n, that's a big problem just right there on its own. To get to n from 2n, we go like this. N goes from 1 to infinity. There's an exponent law that allows us to factor this up and write this as e squared to power n. Reason that works is in this configuration, exponents multiply together. So we can just factor out the n in that way. Divide by 10 power n. And we're getting one step closer. The power should be n minus 1. But at least at this stage, we can say it's going from 1 to infinity of e squared divided by 10 to power n. I'm sensing the need of a border here. Let me just go this way. So we're on our way on this thing. At this stage, we can test for convergence or divergence, but sometimes it's not a bad idea to just get everything in the format we're going for in the first place. So let's go, n goes from 1 to infinity. To drop this to a power n minus 1, we just factor away the base one time. So e squared over 10 divided by e squared over 10 is now to power n minus 1. Well, any questions, folks, with the exponent work we took on this one to get to here? Okay, 11.2 is kind of fun in the sense that it's actually a pretty good review on exponents. So if you feel a little rusty, no worries. These are some of the weirder things that we do, only because this is a topic on sequences and series. So let's take a look at this part next. I guess we use green. Let's keep that color coding going. We have a common ratio R is e squared over 10. We also know e is approximately 2.71. So if you square that, it's less than 9. Or, I mean, calculators are open on the exam. There's no harm in just going to Desmos and analyzing it this way. What is e squared? It's, yeah, quite a bit less than 10. Divide by 10, and we get about 0.73. Either way we look at it, this value, in its exact form, or approximately 0.73, is less than 1. So it satisfies that property in absolute value. It's also certainly less than 1. And we can say here, it converges by, I'll often approximate geometric as just geo, series, test. Any questions, folks, about the convergence on this one? We do. Thanks for mentioning that. So for this problem, there's really two parts. We're going to test for convergence divergence. And if we find convergence, next thing we're doing is finding its total sum. So that's the next step on this one. That's not something we have to do every time a geometric series comes up. So watch out for this in the instructions. The only time you do have to find the total sum is if the instructions explicitly ask you to do so. It does say that in this section because, I mean, we just came up with the geometric series is a thought, I guess. In prior sections, when the geometric series comes up, we don't always calculate what the total sum even is. But here's the next steps. Once I get a proper eraser going, what we need next is the a value. It goes in one spot, right into the numerator. So whatever constant you have factored out, whether it's positive or negative, it goes up above. Let me just move my equality down. So now it's e squared tenths divided by 1 minus, and the thing we subtract off is the common ratio R once again. Again, watch out if there's a negative sign, it could cause double negation here. But with this format, it's just going to be e squared over 10. So that's the total sum. We still have to simplify this thing, but there's a fast simplification. You can just multiply by 10 over 10. That has the effect of clearing denominators so that it's, let me make sure I can fit this here. Yeah, it looks like we have some space. This 10 gets wiped out, just e squared above. This 10 distributes through, so it becomes 10 minus e squared, where it clears that denominator. And so that's the exact form, no simplifications required. We're going for the exact form on these problems, but no harm if you want to approximate it just to see what it might be equal to. But if you end right here, that's what we're expecting on these sections. Well, any questions at all, folks, on getting to this stage? Okay, so that's another convergent geometric series. The miracle in this problem was not only were we able to say it converges, we said what it converged to exactly. That's going to be a pretty rare experience. But let's try this out again. There's a lot of variety on how these problems go. That's why there's so many examples. There's problems where we come up with the formula, problems where the formula is given, and problems where the formula is given, but it's kind of messed up. That's this one right here. So here we have to do a little bit of exponent work. just to make things work out. If you like, you can add some notation to your problems. A common thing we sometimes call the whole series is summation an. Really, that's just a shorthand. And when we write that shorthand, we don't even always put in the lower value, the index starting at 0 going off to infinity. It's just a shorthand to imply that. What it does give us is just a way to reference an without writing down the whole thing every time. But this time we do want to write it down. So if we're trying to get down to that format below here, where it's 3n power n plus 1, we need to factor out 3 squared. So 3 squared factors, it leaves behind 3 to the power n minus 1. Exponents add up in this configuration to get back to n plus 1. And now down below, nothing to do with the 4, but we do need to factor away negative 6, leaving behind negative 6 power n minus 1. Any questions, folks, with those first two steps with the exponents? Yeah.
Since it starts at 0, can you just make it at 1 and then it would change that n plus 1, just n, and then the bottom n to n minus 1?
You know, I like that idea. We're going to have to do that anyway on this problem, even when we come up with this. And going for n minus 1 right now, that might be work we have to erase. So good observation. I wrote this problem myself, but I wasn't looking carefully. The fact that it starts at 0 means we should take a totally different approach. So sorry for the distraction there. The different approach is everything here has to match up. And again, good eye on spotting that there. If it's not a 0, or if it's a 0 and not a 1, we must re-index the series. And re-indexing the series goes just as you said. There's kind of a balance. If we make this go up 1, everywhere you see an n will go down 1. So now it's summation n goes from 1 to infinity. Let's say that here in the notes as well. In the formula for an, n goes to n minus 1. Again, that's only because if we increase by 1, the n values here decrease by 1 to counteract. So right up here, it's now just 3 power n. Down below, 4 times negative 6 to the power n minus 1. And now the work that I was going to do right here, which I just erased totally, is greatly simplified. We just have to factor out 3 to the power 1 to get both n minus 1s above and below. So again, good call on noticing that indexing was messed up on that one. Even if we have things like n minus 1 here, that formula doesn't work if you're indexed off. You could still get convergence and divergence right, but if it converges, we'll get the wrong total sum unless we make that correction there. So next step, let's call this summation as n goes from 1 to infinity. 3. Let's put the 4 down here as well and multiply it by 3/4 power n minus 1. So that 3 that's right here multiplies the power 3, brings it back to 3 power n.
Can it be negative 6 for r? 3 over negative.
Oh, sorry for that weird mistake. Yeah, thanks for capturing that. Negative 6 should have came from here, going into that location, and 4 to 4 in that way. I think we're in better shape now. Any questions at the moment? Okay, well, we've got a couple things. We have a common ratio r. That's this thing. We can say r equals negative 3/6, which is negative 1/2. And good news this time, we can now say the absolute value of r is less than 1, so this converges by the geometric series test. So we have convergence right out of the gate on this thing. We still need to use the 3/4. It'll go here in A for the formula of the total sum. R goes into that location. So now the next steps, just a bit of arithmetic to finalize the problem. So here's how it starts. 3/4 is up above. Down below, it's 1 minus the common ratio. This is really just a negative 1/2. We simplify in this next step. Like before, we can simplify this pretty rapidly. We multiply by something like, say, 4/4. That way, we don't have to necessarily add up any fractions, multiply by reciprocals. You just get 3 in the numerator, and the denominator, 4 multiplies. It's going to be plus in the middle, a 2. So that's after distributing 4 across both terms in the denominator. So now we have 3/6, which means this wild series converges to a value of exactly 1/2. Well, we did, folks. That's pretty much all that's going on with the geometric series. Convergence and divergence is totally resolved here. And just in this section, if it does converge, we're going for the total sum as well. Well, any last questions, folks, on analyzing these 3 geometric series? Okay, let's pause right here for just a moment and take a look at where we're at in the notes. So back over here, I have a document. I think we looked at this, but it was locked behind a paywall on Pinterest or something like that. But this is our convergence divergence flowchart. You could use it for studying problems if you'd like, for homework. I'll move it down on the Moodle website as we go to the further sections. So far, we haven't looked at the test for divergence. We haven't looked at the P-series test, but we're at this level for the geometric series. So that's the one test we've nailed so far. It takes on this format, and convergence is only if the absolute value of the common ratio is less than 1. If you have that, then not only does it converge, but we have the total sum. If this is false, we just say diverges. So if you like flowcharts, that's the purpose of this. And the purpose of chapter 11 is to try to get through all of this stuff on the flowchart. Some of these are going to be more powerful. Some of them are going to be tricky. And that's a tricky one right there. Test for divergence. It's one of the reasons I've revised my notes a whole bunch of times. So let's take a look at that one next. Theorem 6 is not the test for divergence. We're working our way towards it. But it goes back to an observation that plenty of people have made at the very start of these notes. If you're going to add up infinitely many terms and it comes out to some finite number, then those actual terms that you're adding up have to have a limit 0 guarantee. Otherwise, if the limit ever came out to something like, say, 5, that means when n gets large enough, the series, where you're just adding things together, is eventually going to say 5 plus 5 plus 5 plus 5 and so on. It'd be an automatic divergence. So only way we get convergence is that must be 0 in the limit to at the very start. If we take a look at something we just did, like say up here, the common ratio is this thing, and as n goes to infinity, this does go to 0. It's just a negative 1/2. You multiply negative 1/2 by itself over and over and over again, you get values closer and closer to 0. But here's a pretty wild series on this one. Cosine squared of n divided by 1 plus n squared. I said in the example 4, it is known that this series is convergent. Actually, this is something we can test when we have things like the comparison tests. But let's just take this for granted for the moment. That's a convergent series. Given this information, we can do a really complicated limit. We're testing the sequence. Why did sequences come up? Because that's the conclusion of theorem 6. Over here, it's a series written this way. We're still getting used to the terminology, so it's a good idea to always kind of reinforce it in our minds each time we look at these. That's the series. And AN is the sequence. So if we're testing the sequence, we're just using this part of the theorem. We would be taking the limit as n goes to infinity of cosine squared n divide by 1 plus n squared. That is a limit that we could do in section 11.1, but it's kind of tricky. We might want to resort to the squeeze theorem, make estimates on cosine squared. It's at largest positive 1, for example. But we don't have to do any of that because example 4 said this converges. Theorem 6 says if your series converges, so does your sequence. And in fact, your sequence has to converge to 0. So converges by theorem 6. That's an awesome theorem, except that it becomes the test for divergence, and the converse to this theorem is false. Very resoundingly false. So that's the next page we're going to take some careful time looking at, just to get ahead of that major issue. Any questions first, folks, with theorem 6, example 4? Okay, well, let's take a look at the test for divergence. This is an awesome test. And the reason flowcharts like this one put the test for divergence at the very, very top, even though that wasn't the first one we got to, that was the reason it's on the top is because if you're given a random series, say, like this one, that is a very random series. I think most people would agree. If you don't know where to start, the best thing to think about is maybe apply that if you can apply it. Test for divergence. So how does the test for divergence go? It's this. If the limit of an does not exist, or if the limit is not 0, then the series is divergent. This is the contrapositive of theorem 6, essentially. Theorem 6 says, if the series converges, then the limit is 0. Then the thing we said down below here, theorem 6 is the easiest theorem to apply incorrectly in chapter 11. It's because the converse is false. And let's state the converse to this theorem right away. So what we mean by all that is, if we're going to apply a theorem and we want a conclusion of, say, divergent, then we must support the hypothesis part. We must show that either the limit didn't exist or wasn't 0. That's pretty awkward when we go to look at this one right here, because we often want to make that as our conclusion. You cannot do that in theorem 6. The conclusion is just this. So even if you know your limit is 0, you cannot take the conclusion and say it satisfies the hypothesis. That's kind of tragic, but we're kind of tied up with the way this is indicated. This is essentially an, if P is true, P is the whole statement if the series converges, then that's the arrow. Q is true. Q is the statement that the limit converges to 0. So here's the danger in theorem 6. This converse is false to this theorem, and this is what the converse is. The converse goes this way. Q implies P. The statement is wrong, so I wouldn't take offense if you decided not to write on your paper. But if you do write on your paper, make sure you say, this is false. Give a couple extra stars or something like that. The converse would go this way. Limit, if lim, n goes to infinity, of an is 0, then the summation as n goes from 1 to infinity of an converges. Yeah.
What you're saying is if it converges, the limit has to be 0.
Yes, if you know that's true.
0, you have to test if it converges, essentially.
Yeah, if we start with that information, if all we know is the limit is 0, it gives us no knowledge on the convergence or divergence of the series. Really unsatisfying in a certain sense. And that's what this is essentially saying. If the limit is 0, an converges, we took the converse, we switched the order of P and Q, but this is a patently false statement. And that's what we're going to do in part B, show that it's truly false by exhibiting the right counterexample. Anyone happen to know what the counterexample was? It turns out it has a name. It's pretty much the only, among a few named series, This is one specific series that has the name harmonic series. Is a counterexample. For the converse, yeah, the thing that we said is a false statement. So we're showing that the converse of theorem 6, the statement above in part A, which is false, really is false by that right counterexample. So what's the harmonic series? It goes like this. Summation as n goes from 1 to infinity of 1 over n. This, in fact, diverges. We looked at different reasons it might diverge, just graphically with Excel in section 11.1. The author does give a proof of this in section 11.1. We'll prove it another way by using an improper integral in section 11.3. But however we view it, this is divergent. It means you can't actually write down 1 plus a half plus a third plus a fourth, a fifth, and so on, and expect a finite number. It actually goes to infinity, despite the fact that we do know the limit as n goes to infinity of 1 over n is 0. So this is really unfortunate. You can have a limit of 0, be right over here and think the series converges. That's false. We have a limit 0 for the harmonic sequence, and now the harmonic series diverges despite that fact. That's our counterexample. And so the test for divergence is still a really important test, but it only works in this direction. If you get a limit of 0, this test effectively gives you no valuable information at all to solve your problem. In fact, I think that's an important enough comment. Let's say it right down here. If the limit as n goes to infinity of an, the nth term of your sequence, equals 0, then the test for divergence fails. Let's specify a little bit more what we mean by that. We don't mean the test for divergence is a false theorem. It didn't fail in that way. It fails in the sense that no conclusion can be given. Again, that's a really unfortunate fact, because if this thing in red was true, we wouldn't need all this stuff. All this stuff is because the test for divergence works extremely well when it works, but when it fails, we test it as a p-series, if it is a p-series, or geometric series if it is one, or maybe the alternating series test. Probably not that. That's a one-off in this class. Or maybe other things like the comparison test, limit comparison test, and so on. We'll find a lot of tools to get around that unfortunate fact that in part A, this statement is totally false. Well, any last questions, folks? Getting through theorem 7? Okay, we spent a lot of time in this notes, more than the schedule actually even indicated, but I feel like that's because section 11.2 is massively pivotal. It's a good idea, if it feels a little bit vague, to go back to section 11.1, reread it again, even if you're just skimming, read section 11.2 again, and it really helps separate in your mind, what is a sequence, what is a series? So with everything we've done so far, here's all of our tools just collected in a spot. We have the geometric series, the test for divergence that we were just analyzing, and this is carryover from earlier in the notes. If we have, say, summation of a constant multiplying the sequence, constant moves out of the summation, and if we're taking the summation of multiple things like this, we can break into two different series in that kind of way. This is provided, both of those are convergent series in the first place. Well, any questions, folks, before we try out example 5? Okay, so our major tools are really so far, we have a geometric series test, and if it's not a geometric series, try out the test for divergence. And now I'm writing these things down on the actual homework assignment in Moodle, as well as of the examples in class for the lecture notes, because these are essentially the same exact instructions you'll see on a real exam. So we'll analyze these as if they are real exam problems. First, any questions at all, folks, before we start? Yeah. It is a flow chart, but it's not like 100%. You have to follow it directly each time flow chart. It's more along the idea of if you see a random series and you're not too sure what test it is, then consider actually doing the flow chart in order, just as a way to eliminate different tests that may not apply. But it's not to say you always have to go in this order. Other questions so far? Okay, well, example 5 is not too bad in these notes because, again, we only have 2 tests. Looking at this, there's no possibility it's a geometric series. The reason is, in a geometric series, the index n is as an exponent. That's not the case, and here's a base whenever it occurs, not an exponent. So let's start by saying not a geo series. In a certain sense, that's kind of half the battle. We have to decide what series are we even looking at to try to categorize them. So if that doesn't work, we're going to try out the test for divergence. We would take the limit as n goes to infinity of the nth term, which is 3n minus n cubed, all of which is divided by n cubed plus 4. Any volunteers for the value of the limit? How about for someone over Zoom? Anyone see what that limit should resolve as?
I want to say 0 because the denominator is going to get increasingly bigger, and we're going to be subtracting in the numerator an increasingly bigger number. So 0 over a bigger number.
Not quite. This one's going to be a non-zero, it turns out. But you're on the right track. Analyzing the degree in the numerator and the denominator is a definite great way to go. It would turn out to be not 1/4, but you're on the right track still. It would be -1/4 exactly, absolutely. So if you write -1/4 here, or excuse me, it's not -1/4. Just -1, yeah, thanks for saying that. Just -1, sorry about the fourth on that one, it got me too. I think what threw me off is that this is just written kind of out of order, numerator to denominator. I guess just to trick us or something. This one is actually a limit of exactly -1. That's a shortcut that you're encouraged to take, but we haven't done this one a lot, so let's show what the steps would be. You would take limit, n goes to infinity, go only to the denominator exclusively, and pick out the term with the highest degree. That's going to be n cubed. We ignore coefficients if it had one. Now divide everything, numerator and denominator, by n cubed. This won't change equality. We'll just have 3 over n squared on this one, minus 1. 1 plus 4 over n cubed on this one. Related theorem now in section 11.1 says, if you have a constant divided by something to a positive power, that converges to 0 when n goes to infinity. Same with this one. So altogether, we get -1. We're not done with the test, though. The test for divergence says your hope of hopes is that this limit is not 0. Because if it is 0, once again, no information is provided to us on the test for divergence at a limit of 0. But what do we get? We got a -1. Really good idea to put these on your paper. Not equal to 0, because this is forcing you to remind yourself you're on this end of the test, and you satisfied a part of the hypothesis. The limit of the nth term of the sequence is not 0. Then we can say here, I'll use a double right arrow to say this implies, or just another way to say then, series as n goes from 1 to infinity, 3n minus n cubed plus 4, diverges. So we gave a final conclusion of divergence on this one. We did use a test, so for full credit on homework questions and on exam questions, we need to state the name of that test. It feels tedious, but I've taught Calculus 2 for a lot, and I've talked with colleagues about the difficulty with all this information in Chapter 11. The one best advice for students is, even if you're getting tutoring, is write down the name of the test you're using. It forces you to think about those tests. They start to give really good traction in your mind. And this is really more for retention than anything. But also it's helpful for partial credit, since if I know what test you're using, I can assign a partial credit relative to that test. If you just say converges or diverges, and I'm not sure what your work is or what test you used, you could potentially lose even more points. So we always need to state the name of the test we used. This one was test for divergence. And for every test, we have to show all necessary steps. The necessary steps was we have to take the limit, we have to make a conclusion not equal to 0. And really, if you didn't say that part, it just said -1, that would have been okay. But I encourage you to say this part as well, because it reminds you that's the condition which caused divergence in the first place. So that's what a total solution would look like. We gave a conclusion of divergence, we stated the name of the test, and we showed all steps by taking the limit for the test of divergence. Whew, that's a lot of steps, but any questions, folks, on getting through example 5? Okay, again, I'll make a big deal out of this so that when we do these exam questions, it's not a sudden shock of why did I lose points for something small like just indicating the name of the test. So that'll be a pretty decent pattern for each one of these problems. And here's our next one to try out. So, sorry, question first? Yeah, that'd be perfect for me as well. Decent shorthand, except, let me think about that. No, that would be okay. I was a little worried about how sometimes when it comes to, say, like theorem 7, let me think about that for just a moment. You might have to be a little bit more descriptive. Let me remind myself how our author writes out his theorem numbers. In these notes, we have theorem 4, 6, 7. That's kind of unfortunate. So you would have to say theorem 7 of 11.2 or something like that in order to be specific. That kind of sucks. I wish our author said like 7.11 to say theorem 7 of chapter 11, but he does not do that. If you did that yourself, you said 7.11, that would be sensible enough to me that you're saying theorem 7 of section 11.2 or something like that. So that would work out just fine in that case. Other questions so far? Okay, well, let's try out this next one down below. Looking at the format of this one, n is as an exponent. So it looks like a geometric series, but not exactly. There's a couple things going on with this one. This is a case where you might want to split things up. The denominator involves only one term. You could go like this. Summation as we go from 1 to infinity, 4 over 3 to the power of n, plus 2 to the power of n divided by 3 power of n. These look like they're convergent sequences, so we should be allowed to split these up and go summation as n goes from 1 to infinity of this one to start, 4 over 3 power n. They look like geometric series, so let's do a little bit of work on that 3 power of n. Let's make it 3 times 3 power n minus 1. And now same thing on this one, plus the summation as we go from 1 to infinity. This is 2 power of n divided by 3 power of n. So we could write it this way, 2/3 to the power of n. Except we would want to fix that on our next step, make that a power n minus 1. I wrote that kind of weird. Let me write it in this way. But that's our second series now. So these both look like there are, in fact, geometric series, the both of them. So we can start doing some work on them and test for convergence. This one already looks like it converges because it's already showing the common ratio. So the next step, we can write, take your summation as you go from 1 to infinity. On the first series, we have 4/3 times 1 over 3 to the power, oh, and I want to write it this way, 1/3 to the power n minus 1. So even if you just have 3 n minus 1 down below, you can always manufacture a brand new fraction in this kind of way. Does that make sense to folks on this one here? Okay, a little bit less confusing on this one. We're just taking away a factor of 2/3. So it's going to be plus sum from 1 to infinity, 2/3 multiplying 2/3 to a power n minus 1. Now we're in better shape. Yeah, go ahead.
When you, since the n minus one is in the denominator on that three.
Yeah.
Can you just, take it out and just say 1/3? Is that equivalent?
You're saying for,
Like, yeah, right there where, you're just taking out the n minus one, it would be, is it because is it because the exponent is already on the fraction, you don't have to make it negative n plus one or whatever?
oh, I think I see, or, well, first step, not doing too much, we get 4/3, 1 over 3 n minus 1. But even if we factored out the 1/3, 1 over 3 power n minus 1 this way, it would still have the exponent on it.
Yeah.
But is that what you're referring to?
I was just wondering because like normally it's, the exponents have to be negative when it's in the denominator. But is it because, you're putting the exponent on a fraction already? It doesn't have to be instead of on the whole three?
I think I see what you're saying. Yeah. In fact, you could put an exponent on your 1 as well. Go like that as well. But the exponent on the denominator does not have to necessarily be negative. Like say, for example, on this one way up here, way up here, we had a negative on that one, so I take that back, but this one had a positive. So it could be positive or negative on your denominator as well. Is that what you're referring to about the denominator sign?
I think I understand that, and I'm just wording it weird.
Oh, no worries. I do that all the time.
So like, are you able to take the n minus one, out from the three because there's a one on top?
Yes, exactly. So
Because the n minus one to the n minus one is still one.
exactly. So we're essentially creating a fraction, throwing an exponent on it, and saying the whole thing is 4/3 of 1/3 now to power n minus 1 in total. So yeah, it's essentially what you said, the fact that 1 to any power is still just 1 in this setup right here.
That's why we're able to pull it out, swing it down, and it came up.
Yeah, exactly. I think that's essentially what your question was as well. Sorry, I was misunderstanding.
So
But
I-
yeah. Yeah, that was kind of a confusing step going from here to that. So I think the clarification was important. Thanks for mentioning that. The resolution to it was about really putting in a 1 and then to the same power. Well, just any power that's convenient to the problem would work out. But other questions so far? Oh. Okay, well, now we've got 2 series. If one of these is divergent, the whole thing is divergent. I think that might be what happens in the actual homework problem where you see something like this. Strategy is just to split up your series. But now looking at these in this case, let's take a look at our situation. We have a common ratio of 1/3 right here. Satisfies that property. Satisfies that property here as well. So we can say R is 1/3. It's a weird 3 though, less than 1. So this converges. Geo series. This common ratio is 2/3, also less than 1. Reason I always write the less than 1 is it's just a shorthand for this condition. In absolute value, it had to be less than 1 to give convergence. As a geometric series. So now we have convergence on both. We indicated the test just by saying geometric series. You could say geometric series test just to be more specific, but shorthands are just fine as well. So now that we know the whole thing converges, but they're geometric series, we need to do the summations on both of them. So we're taking 4/3 and 2/3. That's the numerator A. And those are going to be the next steps. But any questions to this stage? Okay, so let's focus on one at a time. On this one, we get 4/3. 1 minus common ratio of 1/3 from right here. Let me highlight that a little bit better. Then we go plus and just do the whole thing all over again. Different starting value A, this one's 2/3. Actually, I want to put a little bit of space between these fractions. There we go. So 2/3 on this one, then 1 minus 2/3 down below. And it looks like a lot of fractional arithmetic out of nowhere, but this should be a nice finite value. No harm if you want to just type it into a calculator, but I think it's actually a little bit more accurate for me to just go this way. Putting both denominators on both fractions would give us here just a 4 in the numerator. Distribute the 3 down to the denominator to give you a 3 minus 1. Plus, do it all over again, we'll get a 2. Divide by 3 minus a 2. So this one is 4/2. Plus 2 once. I don't know if that's the right way to say it, just 2. So that's a glorified 2 plus 2, which tells us this mess right here is just another creative way to write the number 4. So if you have to write out a check for $4, you can annoy people really badly that way by just putting this there with a dollar sign. But we've got it, folks. If you have something that doesn't quite fit a geometric series, like this format here, try splitting up your series. It's through the use of this theorem number H right here. There's a lot of different options that can help out. Well, any questions, folks, on maneuvering through this one? Okay, well, let's see what we've got left. We've got some weird things left, it looks like. Cosine of 74 to the power of n is one problem we have. And the next problem is the natural logarithm of 2n n plus 1. We don't have a lot of additional time, but we still want to go in order. But just for the fun of it, does this look like it converges or diverges just by visual inspection? Kind of hard to say, right? Limit of cosine as you go to infinity, say? That one wouldn't exist because cosine is always oscillating.
Is this like an a to the n? Because cosine 74 is a constant?
Exactly. It's basically giving you the common ratio, r. So good eye, you could take cosine of 74. It's about a 0.17. It's not repeating. This one's irrational. But that tells us this is a geometric series in fact. It just looks really, really weird. So good eye spotting that. So we could say cosine 74 is our common ratio r. This is less than 1. In fact, the only way to hit 1 is I need a multiple of, say, 2 pi, something like that. It's cosine 0, cosine 2 pi, cosine negative 4 pi. Those would diverge because we're at either a positive 1 or we can rig a negative 1. But here, strictly less than 1, so this is a convergent geometric series. So if an exam problem tells you to just analyze it this way, your work is done. We gave a conclusion of convergence. We indicated the test by saying it's a geometric series. But in this one section, 11.2, because geometric series are new, we're also looking for the total sum. So let's make this our last problem of the day. First thing we do is we line up the exponent. It has to be a power n minus 1. So we've got a summation from 1 to infinity. of cosine 74 multiplying cosine 74 to the power of 1 less. Now it's ready to converge. Our ratio is that part. Our constant A is just that part right there. So this becomes cosine 74 divided by 1 minus cosine 74. And you know what? Our work is complete on that. There's nothing further to say. So its whole struggle with this one was it just looks way, way abstract. And you know what? I think we have enough time to finish off the last one. First, any questions with this one here? Okay, the reason the last one is so fast is because that is not a geometric series by any measure of what a geometric series is, just alone by n not being an exponent right here. Natural log also totally messes it up. So all we've got in this section is test for divergence now, which means we would take the limit as n goes to infinity of the natural log 2n, n plus 1, but the natural logarithm is continuous. This becomes the natural logarithm of the limit as n goes to infinity of 2n divided by n plus 1. Here's where a shortcut comes into play once again. The limit of this thing, because there's a tie in degree, n above and n below, is just 2 divided by 1, just the coefficients. So this turns into the natural log of 2. Because this is not 0, we've nailed that part of the test for our divergence. So we can say summation natural log of 2n, n plus 1, as we go from 1 to infinity, diverges by test for divergence. That almost sounds redundant, but that's the name of the test for divergence. So these are actually pretty fast problems once we just get a good handling on the tests. But in section 11.3, we get something called the integral test. That is the longest, most drawn out test for convergence and divergence in the whole set of notes in chapter 11. But it's still an important test, and sometimes it's a mandatory test. It's essentially an improper integral type 1. So we'll be reviewing those again when we come back on Thursday's class. Any last questions, folks, before we call it a night?
Well, is there
Okay.
could we say that you have the natural log of 2n over n plus 1? Could that be e to the power of 2n over n plus 1?
You're saying rewrite this function right here?
You're rewriting. Is there any advantage? Yeah.
Limit n goes to infinity. We already had a natural log. So if we throw in e, we have to counteract with a natural log. And then and only then could we put in the other part of the function, natural log.
Okay, all right. I guess I'm I don't quite understand my natural logs very well. So
Good thought, though, if it looked like this, and we want to bring in a base exponential, then we can always manufacture e to the ln, and then throw in that in there. But with the natural log in there already, we wouldn't want to use that strategy necessarily.
Why do we have the extra ln on it?
This right here,
Yeah,
because the cancellation goes this way, and the talk was rewriting this with another base exponential. So if we wrote it that way without that extra logarithm, the new trouble is they wouldn't be equal any longer. It's a different function at that stage. So the only way to make it truly equal is an extra logarithm right there in that spot. Gives equality. Other questions about that? Okay. Well, have a great night, folks. When we come back, we'll be just doing more of this kind of stuff. Test for a divergence, geometric series test. They all start to interact and come up over and over again in the further sections. Well, have a great night, folks. I'll see you all on Thursday.